As ever, I like to go to the researchgate.net website for a summary of the background of the authors of the paper so that I can be sure that the results have been interpreted from a wide knowledge base. Celeste Wilkins, the lead author, is based at the Hartpury University as a lecturer in sport. She has a PhD, 6 publications, more than 1,600 reads, 17 citations. I don't see her expertise areas here. Not sure why they are not stated. And her publications: paradressage, biomechanics, training aid kinematics, rider back pain, posture, and posture in dressage riders. The next author is Jonathan Wheat, who does not yet have a profile listed, and he has one publication, and that is the one that I am analysing today. Lawrence Protheroe is also based at Hartpury College in the Department of Sports Science. He has a PhD in biomechanics, an MSc in sports biomechanics, and a BSc honours in sports science. And he's currently a senior lecturer with 13 publications, almost 4,000 reads, and 127 citations. Skills and expertise are force platforms, kinematics, motion capture, electromyography, sports science, biomechanics, sports biomechanics, movement analysis, and 3D motion analysis. So plenty of tech there. And I'll just scroll through the publications. Catherine Nankervis, if I have pronounced that correctly, is also not listed on the ResearchGate website, but her publications, she has 7, and I will just scroll through those. Saddlery, paradressage, breeding, dressage, dressage, simulators, dressage, and Stephen Draper, also based at Hartpury, has 65 publications, more than 10,000 reads, and 535 citations. He's an academic dean at Hartpury, which is a very senior staff member, and skills and expertise are hypoxia, exercise, exercise physiology, sports medicine, exercise science, exercise performance, oxygen consumption, reaction time, and sports science. And professional placings since September 1998, so almost 30 years. And publications vary from other sporting backgrounds: endurance riding, learning, special needs, posture, physiology, equine hoof conformation, and exercise physiology. The abstract: the rider's ability to consistently coordinate their movements to their horse is a key determinant of performance in equestrian sport. This study investigated the intersegmental coordination variability between the vertical displacement of a riding simulator and the pitch rotation of 28 competitive female dressage riders' head, trunk, pelvis, and left foot in simulated medium and extended trot. They used a 3-way repeated measures ANOVA statistical test and investigated the influence of gait, competition level and segment on coordination variability. They found a significant main effect of gait and segment, however no significant effect of competition level. In medium trot, simulator pelvis coupling was significantly less variable than simulator head, trunk and foot couplings. Significantly greater coordination variability of simulator head and foot relative to the trunk and pelvis suggested that riders can maintain stability in the saddle with their trunk and pelvis while allowing greater variability of their head and foot coupling to the simulator's vertical displacement. They proposed that stronger coupling of the rider's pelvis relative to their other segments is one facet of the equestrian dressage skill of the independent seat. However, greater perturbations during simulated extended trot may necessitate a decrease in the independence of the rider's seat. So what this means is it's more challenging to maintain an independent seat during extended trot. The introduction. Dressage riders aim to give subtle cues so that the horse gives the impression of doing of its own accord what is required. The rider aims to increase the horse's sensitivity to their cues as it progresses in training. They apply pressure with their hands on the reins and through their legs onto the horse's side to cue the horse to change speed or direction. As the horse becomes more sensitive to the rider's cues, the rider can increase their subtlety by giving cues with their seat, by varying the pressure and timing of their weight distribution in the saddle. The subtlety of these cues is contingent on the rider's ability to isolate the movement to their lumbopelvic hip region, known as the independent seat, which aids the rider's ability to stay in balance without relying on the reins for stability and gives the impression of harmony of the horse-rider interaction. And to achieve an independent seat, the rider adapts the movement of their pelvis and trunk to match the movement of the horse's trunk and saddle, while isolating the movement produced during the horse's locomotion to their lumbopelvic hip region to limit the perturbation to their head and hands. Although in a previous paper that I have analysed, the expert rider can use the weight of their head to facilitate engagement of their core muscles and to optimise the stability and in turn synchrony with the horse's movement. The rider's independent seat must also be adaptable to variations in speed within the gaits of walk, trot and canter. And the ability to adapt coordination to various gaits and speeds, which is a necessary component of riding technique for dressage. They must also regulate the horse's movement by initiating strong horse-rider coupling and maintaining low coordination variability to avoid disruptions to the horse's movement pattern. So again, this points to stability and synchrony for harmony. And the coordination should be consistent from stride to stride, but this alone does not reveal the stability of the coordination and how consistent it is between strides. Vertical displacement of the rider's hip was the most in phase with the vertical displacement of the horse's body in a previous study, suggesting that the professional rider was able to dissociate the movement of the horse from that of their hands and head, but maintain a consistent coupling from stride to stride between their segments and the horse, which is the basis for the independent seat. So expert riders can operate, activate, move their body parts separate from their pelvis. And conversely, the novice rider showed significantly larger coordination variability of their head and arm segments, which means they moved more compared with the expert riders. And this reflects their inability to consistently dissociate the movement of the horse from the movement of their trunk and hands. So this would suggest that novice riders would benefit from learning this dissociation pattern off the horse during equitation specific targeted exercise. There is limited knowledge of how riders achieve balance in the saddle, but in studies on a moving platform, the segments closest to the platform are the first to react to perturbations. In other words, for the rider, this would be the ankles and inner thigh together with the pelvis. And it follows that to achieve an independent seat, the rider must anticipate the horse's movement with their pelvic region, likely to be a skill developed with practice. But existing evidence does not fully explain how experienced riders self-organise to respond to perturbations caused by the horse. It is expected that dressage riders alter their technique according to the characteristics of the perturbations produced during locomotion, and riders positioned themselves differently in the saddle to cue the horse to perform slower or faster trot speeds. Simulators may be specific enough to discriminate between experience levels, but it's unclear whether this is still the case between different levels of competitive dressage riders. This study aimed to investigate the influence of segment, competition level, and gait in medium or extended trot on the coordination variability of the rider's segments to the riding simulator. Previous research has identified the pelvis as the main coupling interface, and it is hypothesized that all riders will show the least continuous relative phase variability of the simulator pelvis relationship, indicating strong coupling. In other words, potentially because the pelvis is contacting the simulator surface, possibly with a saddle, they hypothesise that this body region will show the most synchrony with the simulator movement. Previous research tested the relationship between this coordination variability and competition level. So under test here is synchrony for harmony between horse and rider. Methodology: 28 female riders, medium to advanced dressage, including Prix Saint-Georges to Grand Prix, in the 12 months preceding the data collection. They were assigned to one of two groups according to the affiliation of their highest competition level: international, and there were 14 of those, and national, 14 of those. And all were free from riding limiting injuries. The simulator used moved in 3 dimensions, and the movements of medium and extended trot are detailed in table 2. And the key difference is the 40mm increase in the anterior-posterior displacement range of motion, in other words, as seen in the sagittal plane, and small 12.45mm increase in the vertical displacement of the range of motion. So that means basically that the movement was bigger in the extended trot. The frequency of the anterior-posterior motion is slightly faster for the riding simulator than dressage horse stride frequencies previously reported in medium trot and extended trot. However, as stride frequency is related to the size of the horse, variation between horses is expected, and the simulator can be likened to representing an average horse. So just to point out here that the advantage of using a riding simulator in research is that the movement is consistent. Therefore, all subjects are subjected to the same movement patterns, but if they use a saddle, a rigid tree saddle, that can be a confounding variable because the saddle seat surface is going to be a slightly different fit for each rider. So table 2, the linear displacement range of motion and angular displacement range of motion of the medium and extended trot in the anterior, posterior, lateral and vertical directions calculated from the rigid body of the simulator. But were these sensors placed under the saddle region, as in a sensor mat, or placed within the body of the horse, therefore excluding the saddle movement as a variable? Aha! The same standard dressage saddle with a 17.5-inch seat was used for all participants. The stirrups were adjusted to the rider's preference, and there were reins on this simulator, although they were not instructed to maintain consistent tension on the reins during the trial. And the procedure, 9-camera motion capture system, positioned around the simulator so that all markers could be captured in 3 dimensions, and were calibrated so that the origin of the global coordinate system was positioned under the area where the saddle sits during testing. And this coordinate system was defined by the x-axis positive to the rear of the simulator, and the y-axis positioned to the right, and the z-axis positioned upward. Riders wore appropriate equestrian clothing. Spherical markers, 15 mm in diameter, were affixed with tape to the rider's riding helmet, 2 anterior, 2 posterior, 1 on top of the helmet, and the upper trunk attached directly to the skin overlying C7, the left and right acromion processes, the jugular notch, the mid-back and the xiphoid process were attached by an elasticated bandage. The pelvis, left, right, anterior and superior iliac spines, and the body of the sacrum, and the left foot area of the riding boot, covering the lateral malleolus, and 2 on the toe of the boot, 1 on the heel. 3 markers were placed on the rear of the riding simulator. Riders were familiarised with the simulator for at least 5 minutes before the trial commenced. Data was captured for 3 seconds to measure the rider's static position in the saddle, and then for 10 seconds of medium and extended trot respectively, and they were told to ride normally. Data analysis. Rigid bodies were formed from the static capture of the rider for the rider's pelvis, trunk, head and foot, and the simulator. The X, Y and Z axes of each segment was orientated as previously described. Vertical displacement was calculated with software and the signals filtered. Data was split into movement cycles that were defined as the period between 2 consecutive minimums of the vertical displacement of the riding simulator. And there was a control for spurious variability at the start and end of the signal when calculating the continuous relative phase. Coordination variability was assessed by calculating the variability of the continuous relative phase between the vertical displacement of the riding simulator and the pitch of the rider's head, trunk, pelvis and foot. And this vertical displacement was chosen as the signal to which the rider coordinated their segments. But in a live horse, the maximum vertical displacement corresponds to the suspension phase of the gait, while the minimum corresponds to mid-stance. So what this means is that the live horse has a well-defined upward phase of the gait, whereas the simulator may not. Simulator rider coordination was measured over 10 consecutive cycles in medium and extended trot, starting from the third valid cycle, and minimum and maximum values within each of those cycles corresponded to -1 and 1 respectively. Phase angles were calculated for the head, trunk, pelvis and riding simulator segments using software. The continuous relative phase was calculated by determining the difference between the phase angles of the riding simulator relative to the pitch of the rider's head, trunk, pelvis or foot. Coordination variability was then calculated as the point-by-point circular standard deviation of the continuous relative phase for the 10 cycles, which resulted in 28, which were the number of the subjects, continuous coordination variabilities time series of 1001 samples. Statistical analysis software and the coordination variability data was analysed using one-dimensional statistical non-parametric mapping, three-way repeated measures ANOVA, and suprathreshold clusters exceeding 3% of the total cycle were considered for further interpretation. As there was a significant main effect of segment and gait, post hoc SN-PM paired t-tests were conducted between segments and further statistical tests applied for correction. And the results: the three-way repeated measures, competition level with segment with gait, showed a significant main effect for segment and gait. The significant main effect of gait suggests that overall coordination variability significantly decreased at the lowest position of the riding simulator in extended trot, and no significant interactions were found. Post hoc t-tests, figure 3, revealed intersegmental differences in medium and extended trot, respectively. In medium trot, simulator pelvis coordination variability was significantly less than simulator trunk, which coincided with the ascent phase of the riding simulator's cycle. So, in other words, coordination improved with the lift of the simulator's gait and was significantly less than simulator head and simulator foot. So in other words, the feet and the head moved more than the pelvis as the stride ascended in the gait cycle. Simulator trunk coordination variability was significantly less than simulator head, from 0 to 20% of the cycle and 60 to 100% of the cycle. So for part of the cycle, trunk variability was less compared with the head movement. Simulator trunk coordination variability was significantly less than simulator foot, but you would expect that because the foot is in open kinetic chain movement in the main, whereas the pelvis would not be in this cohort of expert riders. Again, in part of the cycle, which corresponded to the downward portion of the rider's simulator cycle. Simulator foot coordination variability was significantly greater than that for simulator head, from 50% to 75% of the cycle. So what we can determined so far from these results is that there is an upward phase of the gait cycle of the simulator and a downward phase, and that coordination variability changes. In extended trot, simulator pelvis coordination variability was less than that of the simulator trunk for half of the gait cycle, but this did not reach statistical significance. So what we can paraphrase here is that in the extended trot, there was less variability for the pelvis compared with the trunk, but not enough to achieve statistical significance. And that the lack of significant suprathreshold clusters within that data set compared to medium trot was due to decreased simulator trunk coordination variability in extended trot. Simulator pelvis was significantly less than simulator head, from 0 to 37% of the cycle, and simulator pelvis was significantly less than simulator foot, from 0 to 100% of the cycle. Simulator trunk coordination variability was significantly less than that for simulator head, from 0 to 100% of the cycle. Simulator trunk was significantly less than simulator foot, from 0 to 100% of the cycle, and no significant differences were found between simulator head coordination variability and simulator foot coordination variability in extended trot. So these results show that there is variability in the coordination of the pelvis and the separate body parts during the ascent and the descent phases of the simulator gait cycle, and potentially where the transition is made between ascent and descent. So with the results stated, we move on to the discussion and implications. And this is a very detailed, fairly lengthy discussion, which is encouraging. They reiterate that they investigated the influence of simulated medium and extended trot, and dressage competition level, and rider segment on coordination variability between the vertical displacement of the simulator and pitch rotation of the rider's head, trunk, pelvis and left foot. And pitch rotation can be seen in the sagittal plane. They hypothesized that the pelvis would exhibit the lowest variability, and this hypothesis was partially accepted as the simulator pelvis coupling exhibited significantly lower coordination variability than the simulator trunk, simulator head or simulator foot couplings in medium trot. But in extended trot, simulator trunk and simulator pelvis was not significantly different, likely due in part to a non-significant increase in the simulator pelvis coordination variability. So something different happens, or coordination variability is lost between medium and extended trot, or it weakens. The significant main effect of gait at the start and end of the simulator's vertical displacement cycle corresponds to an overall decrease in coordination variability between medium and extended trot at the lowest vertical position of the riding simulator. So that may be when the most contact is made, or when the rider can sit in and is momentarily stable, which corresponds with the stance phase in a live horse, where the rider might feel more impact from the horse's movement. The effect of competition level on simulator segment coordination variability revealed that competition level was not significantly related to coordination variability in either gait. And this is interesting because we can't assume that the more expert the rider, the better their coordination or synchrony or harmony is. So the independent seat is important for following the movement of the horse with the lumbopelvic hip complex, leaving the trunk, hands, feet and head to move independently. And this can be related to the rider's ability to achieve dynamic stability in the saddle, which is what I've been emphasising throughout these equitation science papers, is that this all comes back to the rider remaining stable or achieving stability in the saddle. And under these experimental conditions, the saddle seat is going to influence the stability, so that the pelvic floor of some riders may conform better to the saddle that they used than others, or that they may be so familiar with their own saddle seats that they may have preferred their own saddles to the saddle that was used in the study. But it is well worth noting this and keeping it in mind when analysing equitation studies, especially where they don't achieve statistical significance, where they may have expected to, and the results addressed both the rider's independent seat and the cycle-to-cycle variability of the simulator-rider couplings, which relates to the stability of the rider's technique during the dynamic task of simulated sitting trot. Well, I would think they may have displayed better coordination in their own saddles compared with one which was not fitted to them. So this may in fact be about what happens when you use one saddle for 28 riders rather than what happens between medium and extended trot. And to influence the horse, they must achieve consistency in their coupling. If not, this may result in greater variability of the horse's gait. And this coupling cannot be understated, as it allows the rider to stay on the horse during riding. In other words, think of a novice and how much bumping around they do because they have not learned yet to coordinate and stabilise with the horse's movement. And the coordination variability may be a suitable performance indicator, as it corresponds to the rider's ability to influence the horse's gait, rhythm and regularity, which is one of the subjectively judged parameters within a dressage test. And the simulator follows a similar pattern to the horse's trunk in trot, but unlike a live horse, the variability of the riding simulator itself is low, therefore highlighting variability inherent to the rider, which is a very good point and the reason why a simulator is very good for these studies. They may not be exactly the same as a live horse, but what you will get is consistency, so that the rider's movement is isolated, or rider technique is isolated from the variability of the movement of the live horse. In the live horse's trot, the ascent of the horse's trunk occurs at the late stance of the diagonal limb pairs, with peak vertical displacement occurring during the push-off into suspension. And the descent of the trunk occurs from the suspension phase to mid-stance. The rider's trunk and pelvis pitch posteriorly during the ascent phase and anteriorly during the descent phase of the stride in sitting trot. And the simulator follows a similar pattern during its medium and extended trot. In medium trot, simulator trunk coordination variability was significantly greater than simulator pelvis variability during the ascent phase, which we've stated in the results, to the point of the change of direction upward to downward displacement of the simulator's movement cycle. So yes, as the simulator transitions from ascent to descent. No significant differences were found between simulator trunk and simulator pelvis coordination variability from 60 to 100% of the cycle in medium trot, and the same for extended trot in both the ascent and descent phases. And this means that in simulated medium trot, the rider can allow greater cycle-to-cycle variability of the coupling between the posterior pitch of the trunk, while achieving low variability of the relationship between simulator and pelvis. And here they're explaining why there's a difference between the trunk and pelvis. And the descent phase, initiating anterior pitch of trunk and pelvis, appears to be more consistently coupled to the riding simulator in both medium and extended trot. So in other words, the rider goes with the horse simulator or is taken by the movement in the descent phase, but significantly decreased coordination variability in extended trot suggests that decreasing variability of the anterior pitch of the pelvis relative to the vertical displacement of the riding simulator may relate to the rider's balance strategy as the perturbation of the simulator increases. So is there something reflexive going on here with the rider? Significantly greater coordination variability of the simulator trunk relative to the simulator pelvis coupling during the ascent phase of the cycle in medium trot may illustrate a facet of the rider's independent seat in this gait. Okay, so now we're getting to an explanation of the independent seat, possibly where we would expect more movement in the pelvis, but there is less movement in the pelvis and greater movement in the peripheral body parts or segments, which is what an independent seat is. But they're only finding that level or degree of independence in certain phases of the gait cycle. The lower anterior posterior displacement amplitude of medium trot may permit greater between cycle variation of the rider's posterior trunk pitch to the ascent phase of the riding simulator without influencing the stability of the simulator pelvis coupling. So let's just break that sentence down. In medium trot, because there is less upper body tilt displacement, this may permit greater variation of the posterior trunk tilt to the ascent phase without influencing the stability of the simulator pelvis coupling. The large spread of the simulator trunk data in medium trot during the ascent phase indicates individual differences that are likely related to rider characteristics. An example of between rider differences in motor control, standing posture, functional movement test scores, and pelvic posture in the saddle have been reported. And decreased coordination variability between trunk and pelvis transverse plane rotations has been observed in humans with low back pain during walking. Correlations between rider back pain and altered motor control were reported by Deckers et al. Although back pain status or spinal motor control were not measured in this study, variability between these competitive riders may relate to differences in rider trunk control, perhaps influenced by their history of back pain. Yes, recall that the riders declared that they were free from riding limiting injuries. And there is a study which found that expert riders do not consider that their pain levels while riding impacts on their performance. So asking them whether they were free from riding limiting injuries, these riders may not have been aware that pain does in fact limit postural skill. And bearing in mind that a number of studies, including my own, have found pain prevalence in riders while riding to be some 80+%, I think these findings should have been addressed because they are measuring lumbopelvic stability. But at least this study has acknowledged that by stating that the variability may relate to differences in rider trunk control, which may be as a result of a history of back pain. Well, it's not just the history, it's the pain while riding, because they may be relatively pain-free off a horse, but once they actually get into the saddle, sit astride, and are subjected to the forces of the movement generated by the horse, that could influence their lumbopelvic trunk control. Individual differences in the rider's control of trunk posterior pitching moments and the contribution of anthropometric differences between riders could also explain between rider variation. And so could the saddle seat. In extended trot, no significant differences between the simulator pelvis and simulator trunk couplings were apparent, while the significant main effect of gait at the start and end of the cycle suggests that there was an overall decrease in coordination variability, to show a non-significant decrease in the simulator trunk coordination variability, and suggesting that increasing the anterior-posterior displacement of the riding simulator induced greater stability of the simulator trunk coupling. So this means that increasing the displacement front to back induced greater stability of the simulator trunk coupling. And this corroborated with a previous study where, as the frequency of the oscillations increased, the participants' platform ankle coupling and platform hip coupling variability decreased to stabilize their legs. So there's a postural strategy going on here, and that the participants invoked coordination strategies that reflected the challenge of the platform's oscillations to their standing balance. So where possible, the body does strategize to remain upright. For example, at lower oscillation frequencies, the participants invoked an ankle strategy, using ankle flexion to support the maintenance of balance. But as oscillation frequency increased, the participants employed coordinated movements of their hips to centre the mass within the base of support. And this is where the saddle seat surface comes into play, and the consistency of the horse's movement, because it's preferable as a static postural strategy to position the rider's centre of mass over the horse's centre of rotation. And similarly, it appears that riders adopt different coordination strategies depending on the characteristics of the simulator's movement, primarily stabilising their pelvis pitch to the vertical displacement of the riding simulator in medium trot, but increase trunk and pelvis pitch stability to the vertical displacement of the riding simulator in extended trot. So what this states is that there's a different strategy between the medium and the extended trot, and for the extended trot, the rider may increase trunk and pelvis pitch stability in response to vertical displacement. And seated in the saddle, the pitch rotations of the trunk and pelvis are integral to control the position of the rider's centre of mass. So this is about postural skill here, and it's similar to how ankles, knees and hips coordinate when standing. As the simulator's back and forward displacement amplitude increased, so as there was more backwards and forwards movement, there was greater perturbation to the rider's trunk. Yeah, because the body, or the rider's upper body, is a lever that they have to control. So they stabilised its coordination to the riding simulator to maintain balance in the saddle. By extension, this preserved the stability of the simulator-pelvis interaction, not only to stabilise the rider's centre of mass, but also to maintain control of the seat. So getting back to the independent seat again here. Therefore, the pitch rotations of both trunk and pelvis are necessary to maintain balance in the saddle, particularly as the amplitude of the anterior, back forwards, displacement increased. So the rider, it would appear here, must use the trunk and the pelvis to maintain balance in the saddle, not just the pelvis. Simulator head and simulator foot coordination variability were significantly greater than simulator pelvis and simulator trunk in both gaits. In other words, head and feet moved more compared with the pelvis and trunk, and they displayed observably larger inter-individual differences. In other words, some riders moved their head and feet more than other riders, indicating that simulator foot and head couplings are less stable than simulator pelvis and simulator trunk. Yes, because the pelvis and to a certain degree the trunk is more stable because they have a surface to contact. Indeed, decoupling of the head and foot to the vertical displacement of the simulator could be a functional asset that allows the rider to use their legs and feet to cue the horse's gait and direction, allowing their head to remain stable to facilitate visual perception during riding. Well, the expert riders rely on visuals less than novice riders, so that may not explain the strategy for head stabilisation. And for the pitch of the rider's foot, professional riders may use rhythmical dorsiflexion and plantarflexion of the foot, in other words, toes up or toes down, to dampen the movement of the horse during sitting trot. Yeah, tricky one, because if they're not optimally positioned, and perhaps if there is a knee block which interferes with the ankle flexion, this dampening is impeded, compared with not using stirrups. If that were the case for the present population of riders, lower coordination variability of the foot segment would be expected to indicate simulator foot coordination. However, this was not the case. Again, we're putting them in a saddle with stirrups positioned for them, which may not be their preferred choice of saddle seat and stirrup position. Additionally, the rider's foot coordination variability did not significantly increase between medium and extended trot. So in other words, they were able to keep their feet still, but simulator foot coordination variability increased with the gait and may be explained by the decrease in simulator trunk coordination variability. So yes, if you can keep the trunk more stable, then this may help to keep the leg more stable. And for head stability, another study found that the displacement was significantly more variable than their lumbar spine in the vertical and mediolateral axes. In other words, the up-down, side-to-side axes, but not the back-front axis. In the present study, the pitch of the rider's head in sitting trot was analysed, which could explain the contrast between these results and a previous study. Significantly less stability of the couplings between the simulator head and foot relative to simulator pelvis may indicate that these segments may be influenced by other planes or axes of simulator movement. Now, this is where the horizontal translations or horizontal movements come into play, because we know that the riders tend to load on the left seat bone and that the general population tend to have their pelvis rotated clockwise. So the left side of the pelvis or hip is more protracted or advanced compared to the right. It's also possible that the cyclical movement of the simulator, rather than the forward travel and ground reaction forces produced by the live horse, resulted in greater instability of the coupling between simulator foot and simulator head. So they're suggesting that compared with riding a live horse, there is more instability of the feet and head movement compared with the simulator. In the present study, riders were not required to actively cue the simulator to maintain its speed, and therefore this increased variability of head and foot may be related to the task of riding the simulator, where their foot movement or foot motion could remain more passive to the movement. So therefore they need to test this in riders on live horses, which would introduce a whole load more variability to control for. To date, variability in equestrian rider technique has been perceived as detrimental to performance and attributed to lack of rider skill. So they're saying that if a rider cannot sit still, stable and synchronized, then they will not perform well. And as horses and riders are biological systems, some inherent variability can be expected between movement cycles, yes. And previous studies have typically adopted the novice expert paradigm, which infers that the coordination between horse and rider is determined by the single constraint of rider experience. But the task of riding may be drastically different between novice and professional riders. Yes. In this study, the task was standardized between participants by using a simulator, and significant differences between competition level categories for any simulator segment, coordination variability, were not found between national and international dressage riders in this controlled environment. And once riders have entered the lowest levels of national competition, their ability to coordinate with a horse or riding simulator has likely been established, yes. So they're stating here that competitive riders are not usually beginners. So other factors inherent to the rider may have a greater influence on their coordination patterns as they ride passively on a riding simulator. Yeah, it's much easier to ride a simulator than it is to ride a live horse, because you haven't got to consider direction or steering or moderating the speed. All that is removed. Therefore, further research should aim to establish other grouping factors that do not relate to competition level when investigating experienced riders. Now, I would suggest that it's evaluation of the posture and postural skill which separates the novice from the expert riders. and the expert riders from the even more expert riders. Or they could have just had them ride in their own saddles on the simulator. And this study underlined the importance and expanded on the role of the pelvis to the riders' self-organisation as they performed simulated sitting trot and offered a new variable, which was the circular standard deviation of the continuous relative phase. The coordination variability measured the stability of the coordination between the rider's segments and the simulator during the movement cycle. And it is important to note that this variable is derived from the circular standard deviation of the continuous relative phase, which is a higher order variable that compresses the angular rider segments or linear riding simulator displacement and corresponding angular or linear velocity of each coupling pair into a single continuous time series. And this perhaps explains that something reflexive was going on here. The coordination variation indicates the stability of the coordination, but does not provide any information to describe the orientation of the pelvis. Different pelvis orientations may give rise to similarly stable coupling patterns, but may not be viewed as optimal from an aesthetic or injury prevention perspective. Further investigation of the influence of the pelvis orientation on measures of coordination variability is warranted. Well, I'd have to disagree somewhat, because the degree of lumbar curve, particularly in females, may impact on their ability to tilt the pelvis, or such a study may highlight that greater degree of lumbar curve corresponds with greater coordination variability. In other words, we can't just assume that the rider can position their pelvis for stability, especially in a saddle that was not fitted to them optimally. We can't assume that they may perform better. Conclusion: the results captured the underlying variability of multiple simulator rider couplings and provided an insight on one facet of the rider's independent seat: their ability to maintain a strong and stable coupling of the pelvis to the riding simulator while allowing variability between their head, trunk and foot. The pelvis displayed the strongest coupling to the riding simulator, which was resilient to changes in the amplitude of the anterior-posterior displacement from medium to extended trot, and the rider achieved enough stability by initiating coincident movement of the pelvis and trunk so that variability at the extremities did not diminish the rider's stability. Decreased simulator trunk coordination variability in extended trot suggested that the rider maintained the stability of their seat by initiating stronger coupling between their trunk and the vertical displacement of the simulator as the amplitude of the anterior-posterior displacement increased. Therefore, strength of coupling and therefore the independence of the seat may decrease as the characteristics of the horse's gait changes to allow the rider to remain in balance. Further studies should investigate the coordination between horse or riding simulator and riding further, focusing on phase shift and the position of the pelvis to fully characterise the independent seat. Personally, I would pitch rider posture deviations against the ability to achieve an independent seat. To summarise, this detailed study investigated the existence and features of the independent seat tested on a horse movement simulator. The cohort number was low and divided into two groups. Main findings were that riders can maintain stability in the saddle with their pelvis and trunk when controlling head and limb movement, and that there appears to be no marked difference between higher levels of rider ability in medium trot. This suggests that it is highly challenging for riders to distribute the considerable forces generated by the horse in medium trot, even at the higher levels. The riders all used the same saddle, which may have fitted the pelvic floor conformation for some better than others, so it may have been preferable to use the rider's own saddles for best fit to demonstrate independence of the seat. The independence of the rider's seat changed at varying phases of the stride cycle as the simulator transitioned through ascent to descent, and at the more active extended trot gait, the trunk became more stable, potentially as the inherent standing reflex was activated for greater stability. Simulator movement is standardized and does not require any input from the rider to control the horse or any requirement for an independent seat to direct and moderate the horse's movement. Ground reaction forces and excursion would be apparent in the live horse and are elements also not experienced when riding a simulator, which is more of a passive activity for the rider. The study nevertheless demonstrated the potential for the standing reflex to be utilized at phases in the gait cycle where the rider required maximal balance as the body swung back and forth, with the ascent and descent and transitions in between of the simulator. It's plausible that aligning the trunk over the pelvis strategized assisting with core activation, although this was not fully explained by the authors. Again, this is another paper whereby evaluation and individualized exercise prescription of the rider is indicated for precision performance. Finally, this paper has implications for saddle fitting in terms of facilitation of the standing reflex, which could be optimized in saddle design and construction.